Ever pondered the secret behind the mystifying pull of a simple fridge magnet? The answer lies in a fascinating world of materials known as ferromagnets. Let's dive deeper into the world of ferromagnets. These are not your run-of-the-mill materials. They're a unique group of substances that have captivated scientists for centuries. What makes them so special? It's their ability to become magnetized, to exert that mystifying pull we're so familiar with. Now, what's the secret behind this magnetism? It all comes down to the microscopic world, to the very atoms that make up these materials. Every atom is, in itself, a tiny magnet, thanks to the movement of electrons in its shell. In most materials, these atomic magnets are arranged haphazardly, nullifying any overall magnetic effect. But in ferromagnetic materials, something extraordinary happens. The atomic magnets align themselves in the same direction, creating what we call domains. When these domains align under the influence of an external magnetic field, voila, you've got yourself a magnet. Understanding these aspects will give us a better grasp of their mystifying pull. But that's just the tip of the iceberg. There's a lot more to the story of ferromagnetic materials, which we'll explore in the next scene. In the heart of these materials, there's an invisible dance taking place. A dance of tiny particles, the atoms, aligning themselves in a particular direction. It is this uniform alignment that gives ferromagnetic materials their characteristic magnetic properties. This intriguing behavior is not seen in all materials, but only in a select few like iron, nickel, cobalt, and their respective alloys. As we delve deeper into the microscopic world of ferromagnetic substances, we find ourselves in the midst of an atomic ballet. Each atom, a tiny dancer, aligns itself with its partners, creating a synchronized performance that results in the magnetic properties we observe. The lead dancers in this ballet are the electrons, spinning in harmony. This spin creates tiny atomic magnets which line up in the same direction to form what we call magnetic domains. It's these domains that give ferromagnetic materials their unique magnetic properties. Now, most substances have these spinning electrons. However, in materials like plastic or wood, the spins are randomly oriented, canceling out any overall magnetic effect. Herein lies the uniqueness of ferromagnetic materials. Their atomic spins, like disciplined dancers, align in the same direction, creating a strong, uniform magnetic field. This atomic ballet, this dance of alignment and direction, is what sets ferromagnetic materials apart from the rest. It's not just about the atoms or the electrons, it's about the choreography, the synchronization, the harmony that brings about the magnetic magic we witness. The magic happens when these materials are exposed to a magnetic field. The atomic magnets, or spins, align themselves with the external field, creating a strong magnetic effect. What's more captivating? Even when the external field is removed, these spins stay in their aligned position, making the material permanently magnetized. Imagine, if you will, a world invisible to the naked eye, a world of atomic magnets constantly interacting, a world that is the foundation of the mystifying pull of ferromagnetic materials. This is the world of magnetic domains. Magnetic domains are tiny, magnetized regions within ferromagnetic materials. Each domain is like a mini-magnet, with its own north and south pole. When a ferromagnetic material is exposed to a magnetic field, these domains rearrange themselves. Like tiny soldiers, they march in line, their poles aligning with the direction of the magnetic field. This is the process of magnetization. But what happens when the external field is removed, you ask? Well, in most materials, these domains would simply return to their random orientations, and the material would lose its magnetization. But not in ferromagnetics. Here the domains lock into their new configuration, maintaining the magnetization even after the field is gone. This is the process of demagnetization, or rather the resistance to it. Thus, these magnetic domains are the true magicians behind the magic of ferromagnetic materials. They are the ones that make these materials unique, that give them their permanent magnetization. And it is this magic, this unique property, that makes ferromagnetic materials so invaluable to our modern technology. Ferromagnetic materials are not just an academic curiosity. They are the unsung heroes of our modern technology. They are the secret sauce in the hard drives that store our precious data, the transformers that power our homes, the electric motors that drive our vehicles, and the MRI scanners that peek inside our bodies. As we delve deeper into the world of ferromagnetic materials, it's important to realize how integral they are to our modern life. They play a crucial role in our modern technology, often going unnoticed, yet serving as the backbone of our digital society. Let's start with data storage. The hard drives in our computers and servers rely heavily on these materials. The read-write heads of hard drives are made of ferromagnetic materials, which allow them to read and write data by manipulating and detecting tiny magnetic fields. Moving on to power transmission, transformers are another example where these materials shine. The cores of electrical transformers are made of ferromagnetic materials, enabling them to efficiently step up or step down the voltage of electric power. In the realm of transportation, electric motors in vehicles use ferromagnetic materials in their stators and rotors. This allows them to convert electric energy into mechanical energy, propelling our cars, buses, and trains. Finally, in the medical field, MRI scanners, which provide non-invasive, detailed images of the inside of our bodies, wouldn't be possible without these materials. The superconducting magnets at the heart of these machines are made of special alloys that exhibit strong ferromagnetic properties. Without ferromagnetic materials, our modern technology would be vastly different and in many ways less advanced. Their silent yet significant contribution is a testament to the magic of ferromagnetic materials. But the tale of ferromagnetic materials is not just about their magnetism, it's also about their temperature sensitivity. When heated beyond a certain point, known as the Curie temperature, these materials lose their magnetic properties, only to regain them when the temperature drops back. This peculiar behavior is leveraged in a host of applications, from temperature sensors to safety devices in electrical systems. As we delve further into the captivating world of ferromagnetic materials, we uncover yet another fascinating aspect: the intimate relationship between temperature and magnetism. When these materials are heated, they undergo a transformation, a dance of sorts, where their magnetic properties ebb and flow with the rise and fall of temperature. This dance of temperature and magnetism is governed by a special point known as the Curie temperature. Named after the brilliant physicist Marie Curie, this temperature acts as a threshold. Once crossed, the ferromagnetic material temporarily loses its magnetic properties, only to regain them when the temperature descends back below the Curie point. It's as if the material takes a brief intermission from its magnetic performance, returning to the stage when the conditions are just right. This intriguing temperature sensitivity is not merely an academic curiosity. It has practical implications that have been ingeniously harnessed in our daily lives. From acting as temperature sensors in a variety of devices to serving as safety mechanisms in electrical systems, the temperature-dependent behavior of these materials has proven to be a boon for technology. This dance of temperature and magnetism, this intricate interplay, adds yet another layer of complexity to the already fascinating behavior of ferromagnetic materials. It reminds us that there is still much to learn, much to explore in this rich world of ferromagnetics. Moreover, the world of ferromagnetics is rich with phenomena that keep physicists on their toes. The mysterious exchange interaction that leads to spin alignment, the domain theory that explains how magnetization happens, and the intriguing concept of hysteresis that describes how these materials respond to changing magnetic fields. These are just a few examples. As we continue our exploration, let's delve deeper into the mysteries of ferromagnetic materials. The world of ferromagnetics is full of intriguing phenomena. At the heart of it all is the exchange interaction, a quantum mechanical phenomenon responsible for the alignment of atomic spins. This alignment creates a strong magnetic field that defines the ferromagnetic material. Next, we have the domain theory. This remarkable theory explains how magnetization occurs. In a nutshell, it tells us that in ferromagnetic materials, atoms group together into regions known as domains, within which all the spins align in the same direction. When an external magnetic field is applied, these domains grow, shrink, and shift, a dance that results in the magnetization of the material. And then there's the concept of hysteresis. This fascinating property describes how ferromagnetic materials respond to changing magnetic fields. Even after the external magnetic field is removed, these materials retain their magnetization, a phenomenon known as remanence, and it takes a certain amount of reverse field to demagnetize them, a phenomenon known as coercivity. These phenomena, exchange interaction, domain theory, and hysteresis, are what keep physicists on their toes. They make the world of ferromagnetics not just incredibly rich, but also a constant source of fascination and investigation. So, to summarize, ferromagnetic materials are a class of substances that exhibit strong magnetism due to the alignment of atomic spins. They are sensitive to temperature changes, with a unique property of retaining their magnetization even after removal of the external magnetic field. These characteristics make them invaluable in a plethora of applications, from data storage to power transmission, and from vehicle propulsion to medical imaging. So, we've talked about the scientific principles behind ferromagnetic materials, but let's take a moment to appreciate their practical impact on our everyday lives. Their strong magnetism and ability to retain magnetization make them unseen heroes in a variety of applications. Consider your smartphone, for instance. Did you know it contains ferromagnetic materials? They're used in the tiny speaker that allows you to hear your friend's voice, and in the storage memory that holds your precious photos and apps. Or think about your electric car. The motor that propels you along the road uses powerful permanent magnets made from ferromagnetic materials. And let's not forget about the medical field. MRI machines, which provide crucial images of our internal organs, rely on the strong magnetic fields generated by ferromagnetic materials. These are just a few examples. The truth is, ferromagnetic materials are everywhere, silently contributing to our modern world. They are, in fact, indispensable, so the next time you use your phone or drive your car, take a moment to appreciate these unseen heroes. So, the next time you stick a magnet on your fridge, remember the intricate dance of particles that's making it all possible. Take a moment to appreciate the world of ferromagnetic materials, a world that's as fascinating as it is fundamental to our modern lives. As we've explored the fascinating world of ferromagnetic materials, we've come to realize the importance of understanding their behavior. Every time you switch on a device or use any piece of technology, remember that these materials are silently at work, making our modern lives possible. But their role isn't limited to just our everyday lives. They hold the potential to revolutionize the world of technology and science. From quantum computing to advanced medical equipment, the possibilities are endless. With continuous research and advancements in the field, we are just scratching the surface of what these materials can do. So as we move forward, let's appreciate the fascinating world of ferromagnetic materials. Their world is not only fascinating but also fundamental to our modern lives and the future of technology. As we delve deeper into their mysteries, we can only imagine the wonders they hold for us in the future.